Jai Hind students, welcome to my YouTube channel. Students, life is filled with highs and lows, happiness and struggles that will test your resilience and integrity, push you to overcome challenges and leave you with lessons that will make you even stronger on your way up. It's the way you feel and think about yourself, including your expectations and beliefs about what is possible to you, greatly determines everything that happens to you. So students, it all starts with your thoughts. When you change your thoughts, you obviously transform the quality of your life. So as I always keep saying, have that positive approach in your life. Spread positivity, spread happiness, and the same will definitely and certainly return to you, right? So with that, let's start today's session. Today we are going to discuss a very interesting topic, which is the frames of reference, the types of frames of reference, the inertial, the non-inertial frames of reference, right? So first and foremost, we will discuss what a frame of reference actually is. Students, a frame of reference is actually a point of view. For example, for me, this whiteboard, it is at rest. For me, this whiteboard is at rest, no doubt regarding that. But for a person in space, or for that matter a person on moon, this board is in motion. It is rotating along with the rotation of the earth. In order to describe the position of a particle, we require x, y and z axis, isn't it? So these are the axes which is required to describe the position of a particular object or a body with respect to the origin, and also the time of occurrence of an event. That is also very important. So basically x, y, z, these are the three axes which represents the position of a body, and t is the time which is considered the fourth coordinate. So that represents the time of occurrence. So actually frame of reference is nothing but it is the point of view. So frame of reference is a point of view from which a system or an event is observed. In practical terms, it is a set of axes x, y, z with respect to the origin. For location of a point, as I have told you, we need three coordinates x, y and z. If the body is moving in one-dimensional motion, then only one out of these three coordinates required to specify the position of an object completely changes with time. In case of two-dimensional motion, out of these three coordinates, the value of two coordinates will change with time. And in the case of three-dimensional motion, all the three coordinates will change with time, isn't it? So x, y, z, these are the three coordinates which are required to specify the position of a time with respect to origin, right? And time t, for the complete identification of an event, time t is very much required, which is the time of occurrence of an event. So an event is characterized by four coordinates x, y, z. These represent the position of a particular event or a particle or a body, and t is the time coordinate, which is the time of occurrence. It is actually the space coordinates. X, Y, Z, T are known as the space coordinates. So frame of reference is nothing but it is a point of view from which a system or an event or the occurrence of an event is observed. Clear, students? This is regarding the frame of reference. And I must remind you, frame of reference, it is always spoken in relative terms. Nothing in this universe is at absolute rest. Everything is moving with respect to other body, isn't it? I mean, if you consider this pen, for me, from my point of view, this pen is at rest. But imagine a person on moon. From his point of view, this pen is not at rest. It is rotating along with the rotation of the earth. Clear, students? What I mean to say is that the same event can be described by different observers by the different frames of reference differently. Because everything is relative. Everything in the universe is relative. Students, let us discuss the types of frames of reference. There are two types of frame of reference. One is known as the inertial frame of reference. The other one is known as the non-inertial frame of reference. In order to understand inertial and non-inertial frame of reference, let's take the simple example of a huge block lying on a platform. Right? It's supposed to be a railway platform. And let us consider this to be the track, railway track, through which a train runs. Right? So, let us consider three different observers. This is observer A, who is at rest. Let us consider another observer to be sitting inside the train and observing this block, and let the train in which observer B is sitting be moving uniformly. That is, let the train be moving in uniform motion with constant velocity V. Right? And third observer, suppose it is C. He is sitting in another train which will also pass through the same platform, but it is accelerating. It is accelerating in the direction from left to right. So these are the three observers I am talking about. Again, I repeat, students, I have assumed a huge block to be lying on the platform, and I have considered three observers, three frames of reference. One is the person who is also on the platform at rest watching this block. The other one is person B sitting in a train which is moving uniformly from left to right with velocity V, which is constant, right? And third observer C is sitting in another train which is also passing through the same track, and the observer C is also watching this block from the window of his train, but that train is assumed to be accelerating in the direction from left to right with constant acceleration A. Right? Now, from A's point of view, if he wants to describe this block, he will say that the block is at rest, which is perfectly correct, isn't it? Net force acting on the block is 0. Its weight mg will be balanced by the normal reaction which is exerted by the platform on the block in the upward direction, isn't it? So net external force acting on this block is 0. So from this observer's point of view, the block is at rest, which is absolutely correct. In the absence of an net external force, if the block is at rest, it will remain at rest. So Newton's first law is valid from this frame of reference. Now consider the second observer, that is B, who is sitting in a train which is moving with uniform velocity V. So to the observer B, observing this block through the window of his train, it will appear as if the block is moving in the opposite direction with uniform velocity V. Am I clear, students? So, how will observer B describe the event? As per his point of view, he will say that the block is moving uniformly from right to left with constant speed V. Right? So here, from B's point of view, that is from his frame of reference, again the Newton's first law is valid, because in the absence of a net external force, if the block is in uniform motion along a straight line, it will remain in uniform motion along a straight line. So from frame of reference A, and in the case of frame of reference B, which is the train which is moving with uniform velocity, in both the cases Newton's first law is obeyed. Right? That is, law of inertia is obeyed. Now consider, student, observer C, who is assumed to be sitting in a train which is accelerating with constant acceleration A. Train is accelerating. So to observer C, watching this block through the window of his train, it will appear as if the block is having acceleration along this direction. So to him it will appear as if some fictitious force is acting on this block, which is making the block to accelerate in the opposite direction. But the fact remains, no net real force acts on the block. But still, to the observer C, the block appears to be accelerating in the opposite direction. So from his point of view, he will say that the block is accelerating with constant acceleration A in the opposite direction. Right? So these are the three observations made by observer A, observer B and observer C. In the case of observer C, when it is taken as a reference, frame of reference, then Newton's law, first law, is not at all valid because no real force acts on it, and still the body appears to be acted by some pseudo force, as a result of which the body appears to be accelerating in the opposite direction. So in respect of frame of reference C, Newton's first law of motion is not valid. While in respect to frame of reference A and B, Newton's law is found to be valid. So students, frame of reference A and frame of reference B, which was either considered to be at rest or in uniform motion, those were the frames of reference where Newton's first law is valid. And these frame of reference are known as inertial frame of reference. Right? While on the other hand, in case of C, which is another frame of reference, which is accelerating frame of reference, in that case Newton's first law of motion is found to be invalid. It is found to be not valid at all. That is, in an accelerating frame of reference, some pseudo force, some fictitious force comes into play. So that frame of reference is known as non-inertial frame of reference. Clear, students? We will consider some other examples as well. Let's consider some other examples as well. Let's talk about non-inertial frame of reference. We have experienced various examples to elaborate this existence of fictitious or pseudo force. Suppose, students, a vehicle is taking a turn. Suppose you are sitting in a bus and the bus is taking a sharp turn. So the passenger sitting inside the bus will experience a force in the radially outward direction. That is centrifugal force. It is actually a pseudo force. It is actually a fictitious force. While taking a circular turn, the bus will act as a non-inertial frame of reference. Why it will act as a non-inertial frame of reference? Because while taking the turn, the bus will have acceleration. So it is having acceleration, and hence that frame of reference will be known as non-inertial frame of reference. So in that case, a fictitious force will exist, and in this case it is known as centrifugal force. So this is known as pseudo force, pseudo or fictitious force. So in case of a turn, the passengers sitting inside the bus experience a force in the radially outward direction. Centripetal force acts in the radially inward direction. Centrifugal force, which is the pseudo force in the non-inertial frame of reference, acts in the radially outward direction. Right? Another example, students. Let's consider the case of a passenger sitting in a bus which initially is in motion and the driver of the bus suddenly applies brake. Then we are aware the passenger will experience a force in the forward direction. Isn't it? So, as the driver of the bus applies brake, the bus will behave as a non-inertial frame of reference because it is retarding, it is having negative acceleration. So as a result, a fictitious force acts on the person sitting in the bus, which will make the person move forward. Isn't it? So that's the proof of the existence of pseudo force or a fictitious force. It is just developed so as to explain the phenomena. Similarly, when the bus suddenly starts from rest, we experience a force in the backward direction. As soon as the bus starts from rest to motion, it is getting accelerated. So again a force acts on the person sitting in the bus in the backward direction. So in that case, again the bus will act as a non-inertial frame of reference. So the concept of pseudo fictitious force, it exists only in the non-inertial frame of reference. There are some other examples as well. Let us assume this to be a truck and a block is placed at its back like this. Suppose a block is placed and we are considering the ideal conditions. We are considering the ideal condition. This is the truck. In case, students, the truck is at rest or is moving in uniform motion along a straight line, then the block will remain at rest. That is, in case the truck is at rest or possesses uniform motion along a straight line, in both the cases it will act as inertial frame of reference where the Newton's first law, that is law of inertia, will hold valid. So in that case the block, if it is at rest, it will remain at rest only in the absence of any net external force. But have you ever imagined what will happen if the truck starts accelerating along this direction? What will happen is this block will experience a fictitious or a pseudo force in the opposite direction. So if its mass is m, it will experience a fictitious force ma in the opposite direction. So here, although no real force acts on it, but still the block will move in the backward direction. So in order to explain this phenomenon, the concept of the pseudo fictitious force has been considered. Clear, students? So as the truck accelerates, it will act as non-inertial frame of reference, because that frame of reference which is accelerating or which is rotating, rotation also causes acceleration. So either the frame of reference must be rotating or it must be having linear acceleration. In that cases, the frame of reference under consideration is known as non-inertial frame of reference. In non-inertial frame of reference, this fictitious or pseudo force does exist. Right? Let's consider another example. Suppose this is an inclined plane. If this angle is greater than the angle of repose, then a block kept on the inclined plane will certainly slide down, isn't it? If I want that this block remains stationary with respect to the inclined plane, then I should impart the entire system comprising of this inclined plane and the block an acceleration in this direction. So now, when I give an acceleration A in this direction to the system, then this block, say of mass m, will experience a pseudo force ma in the opposite direction. Right? So this force may prevent the block from sliding. Clear, students? So again, it is the case of accelerated system, so it will act as non-inertial frame of reference, and thus the existence of pseudo force, which is the fictitious force. Another example. Let's consider this to be a block A, and let us consider this to be block B. If I intend to keep the position of B with respect to body A as fixed, if I want that block B do not slide down, then I must provide an acceleration to the system in this direction, so that the block B of mass m experiences a fictitious force in the opposite direction. So this fictitious force might help in preventing the block B from sliding down. Clear, students? So it is when the system is accelerated that the body inside the system experiences a pseudo force in the opposite direction as that of the acceleration of the system. Right? You must remember the case of elevator. There's another example. So in case students, the elevator is at rest or the elevator is in uniform motion, then a person standing on a weighing machine inside the lift, in that case the apparent weight is found to be exactly equal to the true weight of the person, isn't it? But what happens is, in case the lift moves forward, so now what happens? The person or the block of mass m, if the system is accelerated upwards, then it will experience an additional force ma in the downward direction. Am I clear, students? This is the fictitious force, and this is in addition to the weight of the block. So now net force acting downward would be ma plus g. So net force acting would be mg plus a. This is the net force acting downwards. Am I clear, students? As a result, what will happen? The net weight of the person will tend to increase. Apparent weight of the block or the person will be greater than that of the actual weight. So this is the thing. If we consider the elevator to be coming downwards, suppose this is the person or the block and the elevator is coming downwards with acceleration a. Now, the entire system is being accelerated, so it will act as a non-inertial frame of reference. So fictitious force will come into play. So the fictitious force, as I mentioned in all the above examples, fictitious force exists in the non-inertial frame of reference, which must be accelerated one, right? And in that case, the body inside the system will experience a force, mass multiplied by the acceleration of the system in a direction opposite to which the system gets accelerated. So here the system is getting accelerated in the downward direction. So this body inside the system will experience a force ma in the upward direction. And obviously its weight will act in the downward direction. So these two being opposite, the net downward force, net weight, it would be mg minus a. In this case, net force would be mg minus a. So when the elevator accelerates downwards, then the apparent weight of the person is less than that of its actual weight. So students, these all are the examples of non-inertial frames of reference. And as I've told you, non-inertial frame of reference means a frame of reference in which the frame under consideration must be in acceleration. It must either have linear acceleration or it must be rotating, because rotation does cause acceleration, right? While on the other hand, if the frame of reference is at rest or it is in uniform motion, then that is known as inertial frame of reference, where Newton's law of motion, first law, that is the law of inertia, is valid. Students, now let us watch a very interesting video. Whatever I have explained theoretically, now I have created an animation, right? So try to understand this. It will clearly elaborate about the inertial and the non-inertial frame of reference. So let's watch this animation.
Let us consider a ball to be bouncing as shown in the video. In this case, the truck is at rest. It is an inertial frame of reference where Newton's first law, that is law of inertia, is valid. Now suppose the truck is moving along a straight line with uniform velocity. This is also the case of an inertial frame of reference. If we consider the truck to be accelerating in the forward direction, then the ball will experience a pseudo force which will make it move in the backward direction. And if the truck applies the brake, then the ball will experience a forward pseudo force. So, an accelerating frame of reference where pseudo force acts and no real force acts is known as a non-inertial frame of reference.
So I hope you have enjoyed watching this animation, right? So let us try to recap all the things which we have studied till now in this session, right? We have discussed about the frame of reference. It is actually a point of view of the occurrence of an event, right? And then we have discussed types of frame of reference, inertial and non-inertial. Inertial frame of reference is that frame of reference which is either at rest or in uniform motion along a straight line. While on the other hand, non-inertial frame of reference must be accelerated one. And acceleration can be obtained either linearly or through rotation, isn't it? So whenever a frame of reference under consideration is either rotating or having linear acceleration, then it must be non-inertial frame of reference. In the case of inertial frame of reference, only real forces act. While in the case of non-inertial frame of reference, we have discussed in so many examples, pseudo or fictitious force comes into play, right? And third, most importantly, students, inertial frame of reference is that frame of reference in which the law of inertia, which is Newton's first law of motion, holds good or it is valid. While on the other hand, in the case of non-inertial, that is accelerated frame of reference, Newton's first law of motion, that is the law of inertia, is not valid, right? Again, let me elaborate with a very simple example. This is suppose a beaker and is half filled with water. In case it is kept in a vehicle which is at rest and it is placed on a perfectly horizontal surface, then the level of water would remain like this. Am I clear, students? And even if the vehicle, if it starts moving, and let us consider the vehicle to moving with uniform velocity along a straight line, then also the level of the water in the beaker will remain same. Clear? Now imagine the same vehicle to be accelerating in the forward direction. Same vehicle to be accelerating in the forward direction. Then what happens? The liquid inside the beaker will experience a fictitious or a pseudo force in a direction opposite to which the system is getting accelerated. So as a result of this pseudo force, what will happen is the level of the water will become somewhat like this. So this is a simple observation which you can yourself observe in your daily life, right? So this is basically due to the existence of pseudo force in the non-inertial frame of reference, while it is the case when the system is either at rest or in uniform motion. So it is the case of inertial frame of reference, while the existence of pseudo force is in the case of non-inertial frame of reference, right? Now a very important point arises, student. Frame of reference which is either rotating is non-inertial. So by the definition, strictly speaking, Earth is rotating about its own axis. So Earth does possess acceleration, which is the centripetal acceleration. So it must be considered non-inertial frame of reference, isn't it? Again I repeat, students, Earth rotates about its own axis and the sense of rotation is from west to east. So since the Earth rotates, therefore it must be having centripetal acceleration, and any accelerated frame of reference must be non-inertial. So strictly speaking, Earth must be treated as non-inertial frame of reference. But still, for all practical purposes, Earth is considered to be inertial frame of reference. So in order to elaborate or in order to explain why Earth is considered to be an inertial frame of reference, again, let's watch this short video.
We know that an inertial frame of reference is that frame of reference which is either at rest or in uniform motion. Now, is the Earth frame really inertial? Let's try to answer it. We are aware that Earth rotates about its own axis, and the rotation causes acceleration. And Earth rotates about its own axis with an angular speed omega, which is 2 pi by capital T. Capital T is the time period, that is the time taken by the Earth to complete one rotation, which is approximately 24 hours. So, as the rotation of the Earth causes acceleration, therefore let us find out the value of the centripetal acceleration. Radius of the Earth is 6400 kilometer, and as I have said, the angular speed is 7.27 into 10 to the minus 5 radian per second. Substituting the value of omega and r, we can easily get the centripetal acceleration, and it comes out to be about 0.034 meter per second square, which is actually very less as compared to the acceleration due to gravity. The centripetal acceleration as well as the acceleration due to gravity, which is due to the force of gravity, both acts in the radially inward direction. And since centripetal acceleration is very small as compared to the acceleration due to gravity, thus the effect of rotation of the Earth on the acceleration due to gravity can be a sort of neglected. Thus, strictly speaking, the Earth's frame is also a non-inertial frame because of the fact that Earth is rotating, and thus it's the case of accelerating frame. But due to the negligible effect of the Earth's rotation on the acceleration due to gravity, therefore Earth can be considered to be an inertial frame of reference.